Okay, in this video, I'm going to be going over what I've been learning lately, which is about using implicit differentiation to find related rates and solve equations. And so before I go into solving word problems, I think it's helpful to just do a quick review of how we differentiate functions with implicit differentiation with respect to time. So let's look here at the question. It says, assume that x and y are both differentiable functions of t and find the required values of dy dt and dx dt. So and it tells us to assume that they're both differentiable functions of time. So we'll see when we do the word problems, it's more implied that we're talking about that, but we are practicing the groundwork of how to do that. So we're given this equation, and it says y equals the square root of x. I'll tell you what, let's go over what is a related rate. So I think we should start there. So what is a related rate? Well, I see the word rate, and I know that that means derivative. So if I look at our problem, y equals square root of x, I know that I could be talking about dy dx or dx dy. But related rates are a special group of differentiation problems. When we're doing a related rate, we're not differentiating with respect to any of the variables in this equation. We are going to be differentiating with respect to time. That's the dt there. So I know that x and y here are related to each other. And that's what, we're talking about when we're talking about this. They have this relationship. And I'm going to differentiate both sides of my equation, keeping in mind that I am differentiating with respect to t. So you have to differentiate both sides. So we have the derivative of y is just 1. Let me put this up here. It's just 1. But I'm also differentiating, taking the derivative of y with respect to time. So I have to put dy dt. Now another way of writing square root of x is x to the 1/2. So let's do it that way because it just makes it a little bit easier to see what we need to do to take the derivative of that. So if you don't remember, I'll do a quick aside over here. That when you have x to a power, the derivative of x to a power, you bring the power down, and then it's 1 minus the power. So I have x to the 1/2, I bring the 1/2 down, I have x, and then I'm saying 1 minus 1/2, which is going to give me a negative 1/2. Okay? There we go. Let me... so big. Okay. Now, I'm not done though because I also have to take the derivative of x with the respect to time. Okay, so now I have dy dt equals 1/2 x to the negative 1/2 dx dt. Okay, so I am trying to find dy dt when x equals 4. This bar is just another way of saying when x equals 4. And so what I'm going to do is I need to isolate dy dt. Well, this problem already has dy dt isolated, so I can go ahead and plug in my values. And I have 1/2 x is 4. Remember, it's right here. We're doing a. Just put that a. To the negative 1/2. And then dx dt, instead of rewriting that, I'll just plug it in. Dx dt is given as 3. Okay, now remember when we rewrote square root of x as also equaling x to the 1/2, well, if I have x to a negative 1/2 or anything to a negative, that's just like saying that it's in the denominator. And remember, the same, when you have 1/2, that's just the square root of. So that would just be in the denominator. So that is what we're going to do up here. We're going to do a procedure that is very similar to that, just with different numbers. Okay, so I have 4 to the negative 1/2. So that means I have square root of 4 in the denominator. Now I also have a 2. So let's put my 2. I can put my 1/2 just like that. So my 2 is in the denominator. And then I have a 3 in my numerator. So 3 times 1 equals dy dt. So then let's clean that up, and we have 3 to square root of 4. Now this can be simplified more, because what is the square root of 4? Well, that's 2. So 2 times 2 equals 4. And that is the derivative of y with respect to time when x equals 4. Now, let's look at b. We want to find dx dt this time, so it's going to be different. When x equals 25 and dy dt equals 2. Now, even though the information that we're plugging in is different, the derivative of y equals the square root of x is always going to be the derivative of y equals square root of x. So we have the derivative of y, which we already said was the derivative of y with respect to time. And then we have the square root of x, which is 1/2 x to the minus 1/2 times the derivative of x with respect to time. Now, we need to isolate the variable that we're looking for, which is dx dt. So what I'm going to do is I'm going to have dy dt divided by, I need to divide that guy away. So we're going to have 1/2 x to the minus 1/2. Well, he's already a minus 1/2 guy, so we're going to rewrite him because he belongs in the denominator anyways. Whoops. So we're just going to go like that. 1/2 square root of x equals dx dt. Now our dy dt is going to be 2. So we have 2 1/2 square root of x, which is, what is square root? X is 25 here, equals dx dt. Okay, now we can solve for this without using a calculator, or you could use a calculator, but remember, when you're dividing by something, that's the same as multiplying by its reciprocal. So we can say 2 times, now this reciprocal looks like this, or excuse me, not the reciprocal, but right now, what this looks like is 1 over 2 to the 25th, because this 1 is in a numerator, so he's part of the numerator. So what you can do is flip it. The reciprocal is just flipping it. Okay, so we're going to flip. We're going to say 2 times 2 square root of 25. 2 is over 1. He's over 1. This is going to give us 2 times 2 with square root of 25 times 5 all over 1. Okay. That means the derivative of x with respect to time is 2 times 2, which is 4, times 5, which is 20. That's 20. Okay, so these are the kind of problems that we're going to be doing. I want to do a few more. Let's see. Let's do... This is a good one because it brings up a good point. Let's do... Find dy dt when x equals 3, y equals 4, given that dx dt equals 8. Okay, so we have x, y equals 4. Now what we have right here is a product. So we have to use the product rule of differentiating, which, as an aside, if we just were using the product rule, this would be we would do the derivative of this is the first and this is the second function. So we would say, or not function, the second part of our product here. And so we would say the derivative of the first, which would be 1, and then you just write the second, times the second. Hold on, let me make that a little bit neater. The derivative of the first times the second, just how he is, plus, okay, when we're using the product rule, we use a plus, times the derivative of the second, which is 1, times the first, just as he is. So that's what we would do, and of course, the constant is just always 0. So if this was just a straight up product rule, that's what we would do. But remember, we are assuming that these are all derivatives, that they're differentiable functions of t. So what we're going to do then is we will take the derivative of the first, so derivative of the first, but remember, it's not just 1 now, it's also the derivative of x with respect to time. Oops, don't close that yet. Times the second, which is just y, plus the first, just how he is, times the derivative of the second, which is 1, times, remember we have to also differentiate y with respect to time, equals, and that's still 0. Constant is always 0. So derivative of a constant, always 0. Okay. So let's clean this up a little bit. So we have dx dt times y plus x dy dt equals 0. Okay, and we are looking for dx dt. So what we want to do is we want to isolate what we're looking for. So dx dt. So we will say minus, I'm just going to minus this whole guy away to the other side. So we'll have minus x dy dt. Oh no, I lied. This says find dy dt. So we'll do that first. Sorry about that. Oh wait. Okay, so we're then just going to minus him. Minus this guy away, the y dx dt. So we have minus y dx dt. And then we have left, I'll just write it, x dy dt. We need to divide x away. So we have over here, I'm going to put this in red, that dy dt equals negative y divided by x dx dt. Okay. So now we need to find, so let's find dy dt when x equals 3. Okay, so we have our derivative is dy dt equals negative y, which is 4, over x, which is 3, times dx dt, which is 8. I'm not sure what I did with my calculator. Oh, sitting on it. Okay. So, -4 divided by 3 times 8. This is going to be -10.7. So that is dy dt when x equals 3. Now, let's see. We could keep going, but I think that, oh, let's do one more part. Let's say, find dx dt. So we're going to be using the same equation when x equals 1 and y equals 4 and dy dt equals -6. Okay, so we have the same equation, which is xy equals 4. And we can take the derivative that we have here and we can just rearrange it real quick. So we have dy dt equals -y over x dx dt. But now we want dx dt by itself. So what we're going to do is we're going to multiply both sides by x. And then you get, let me do it in a different color. Multiply both sides by x. So there we go. And then you have x dy dt equals -y dx dt. And so you can also then say divided by -y. And that is going to equal dx dt. So it's going to be the same derivative. We just have different informations, and then we rearrange it based on, the exact derivative that we want. Okay. So now that we have our derivative, what are we trying to find? We're trying to find when x equals 1. So we have -1 because we're just plugging in here. So -1, y equals 4 times dy dt, which is -6, which you could use a calculator also, but this is just like saying -1 over 4 times -6 over 1. That -6 is considered to be in the numerator, right? So we can just easily go, 6 over 4, which we can further simplify into 3 over 2, and that is what our dx dt is at these moments in time. Okay. And then let's do another one. Yeah. Okay. Let's do green. Okay, so we'll say a point is moving along the graph. Feel free to fast forward through this writing part if you need to. Along graph of the given function at the rate dx dt. Find dy dt for the given values of x. I find it's helpful to write the problem out when I'm doing my homework instead of just reading it. I have a teacher that when she lectures, she writes things out, and I find that that is just one of the ways that my brain can have time to absorb what's being asked. Okay, so here is our equation. We'll say y equals 2x squared plus 1. Our dx dt equals 2 centimeters per second. Now, if you'll look here, the derivative of x with respect to time is literally the distance x per time. So it's a rate. Okay. Now we're given the first value that we're given is x equals -1. And then we'll have for b, x equals 0. And then, I don't know if I have enough room. Probably not. I might be pushing it. Okay. So in this problem, they give us the curve y equals 2x squared plus 1. And they give us a point moving along that curve. They give us how fast that curve is moving in the x direction. And that's represented by the dx dt equals 2 centimeters per second. They ask us how fast it is moving in the y direction. That is what find dy dt means. Given these current x values, our job is to find these different rates of change for the y variable. So let's do it. Okay, so we have to first differentiate our equation. Do not plug in your values before you do that. So we have the derivative of y with respect to time equals, we have to do our regular derivative first, then times the derivative of x with respect to time plus 0. Derivative of a constant, always 0. Okay, so this equals 4x, and dx dt is 2. I guess I'm plugging x. X is -1. And that is the rate of change for the y variable at this point in time. So we have -8 is our rate of change for the y variable when x equals x equals -1. So that's our first part. I'm going to move this x equals 0 over a little bit more, so that way we'll have some more room. Okay, so same derivative. So it's going to be dy dt equals 4x dx dt. And then we plug in 4 times 0 times dx dt, which is 2. Well, anything times 0 is 0. All right. So now let's do over here. We have dy dt equals 4x times dx dt. And then we plug in our values. So we have 4 times 1 times 2. And so we see here that this is 8, which if you look at this, I'm guessing this curve is a parabola because it's squared, right? So if you look, when I'm not exactly, I haven't had a professor tell me that this is correct, but I'm guessing that at x equals -1, we have it down here. Here's our origin, right? We'll say that's our origin. I'm totally guessing on this too. But say we have negative, when x is -1, the rate of change down here is -8. And then when we have x equals 0, we also have a rate of change of 0 for y. And then when x is 1, we have it at 8. So maybe then our parabola is going up. I don't know. If somebody knows in the comments, let me know, because I'm kind of curious now. Kind of want to know. Okay. Stay curious, right? So I don't know that for sure, but I'm just wondering. It's kind of interesting. Okay, moving on. All right, so now let's look at, okay, let's do one with some trig. Okay, so let's do y equals tan x dx dt. Just joking. I need to spread that out some more. Dx dt equals 3 feet per second. And we want to find dy dt for given values. For ... Let's do a is x equals -pi/3, and b, I'm going to need more room on this, -pi/4, because I want to show you something. Okay, so we have our function. We need to differentiate it. So the derivative of y with respect to time is dy dt. Now, the derivative of tangent is secant squared x, but we also have to take the derivative of this x with respect to time, so it would normally just be 1, but now we have the derivative of x with respect to time. Okay, so we need to look at let's go ahead and let's plug in let's look at our unit circle, because we're going to be looking for -pi/3. Well, just as a quick aside, we have this is pi/3 up here, and so that's not the best. We'll have -pi/3 down here. Okay, so it's really helpful if you just remember these three things. So we have pi/3, pi/4, and then pi/6, right? So the very first for pi/3 is 1/2 square root of 3/2. And then for this, it's root 2, 2, root 2, 2. And then for down here, it's just the flip of these, which is square root of 3/2, 1/2. Now, as you're going around the unit circle, this pi/3 is just going to switch signs depending on the quadrant. So in this fourth quadrant, we're going to have our cosine is going to be positive. So we still have 1/2, but our sine is negative. So those are our values. So -pi/3 is 1/2. But what is the secant? Right? So we know cosine, right? This is cosine. This is sine. So I found this really helpful. So if we have secant, what does secant go with? Secant is the reciprocal of cosine. So if we do 1 over cosine squared x, that's the same as secant squared x, right? Right. Times dx dt. Well, now we know what that is. We know what cosine is. It is 1/2 squared. That's what this is down there, right? And so times dx dt. Dx dt is given as 3. So remember we talked about dividing. We can also just go ahead and square this. So 1 squared is 1. 2 squared is 2. So then if I were to multiply by the reciprocal of this, it's just going to be 1 times 4 over 1, right? So then this gets super simple, super fast. When you know your unit circle, things get so much simpler and they don't have to feel scary. I spent a weekend just going over and rewriting this unit circle a bunch of times. And I still messed it up the other day. So it's okay to mess up. Just go back and practice, practice, practice. I heard that Einstein said that he wasn't particularly smart. He was just obsessed. So just keep at it. Okay, so then we have that dy dt equals 12 feet per second. How cool is that? That we were able to figure that out so easily, just by knowing that. Okay, so then let's look at negative pi over 4. So we're having the exact same, remember, so negative pi over 4 is going to be like right in here, right? And what is our pi over 4? The cosine for our pi over 4 is square root of 2 over 2. Okay, so if we have dy dt equals secant squared x dx dt, then that means we have 1 over cosine squared x times, oh, you know what? I just realized I made a mistake, which it hasn't affected our problem, but actually, no, I didn't. I thought I did, but then I realized I didn't. So I retract that statement. Okay. So dx dt equals 1 over, and then we're going to have square root of 2 squared times dx dt. Okay, so we're going to have 2 over 4. 1 over 2 over 4, because I just squared the 2, which makes it 2, and then I squared square root of 2, which anytime you square a square root, you just get the number, and then 2 times 2 equals, is 4. And then we have dx dt, which is 3. So let's multiply by the reciprocal. So we have 1 times 4 over 2, which is what? 2 times 3 equals 6. And that is our derivative of y with respect to time when x is negative pi over 4. Super cool, right? Super cool. And then we can also do x when x is 0. So this is just, I guess we don't really need to do it, but I guess we can. If I can get my pen to work. So if I have, when x equals 0, I'll do a different color. And we have the same derivative. We have dy dt equals secant squared x dx dt, and dx dt equals 3. So here it's also going to, we're just going to do 1 over cosine again. Well, what is our cosine here? It's just 0. Right? That's not a thing. So we could also just do it simply like this and say 0 times 3, which equals 0. So that's what our dy dt would be when x equals 0. Okay. And then I wanted to do one fun problem with you. And then I'll probably make a video doing more. So now we're going to see how these rules of differentiating can be applied to word problems. So we have, I think I'm just going to do one. Okay, and we're going to be finding the rates of change, aka derivatives, right, of the area when r equals 37 centimeters. Okay, so let's look at this problem. The radius of a circle. So we're given so much information like as soon as the problem starts. So we know we're going to be working with a circle. And it's increasing at a rate of 4 centimeters per second. So this is telling you, it just gives it to you, that the rate of change of r with respect to time, aka dr dt, equals 4 centimeters per minute. Now, it wants us to find the rate of change of area. So it wants us to find dA dt when r equals 37 centimeters. So we don't know that yet. So how do we find this out? Well, they're going to expect you to know your areas and your volume equations for all of these problems. Like I only had one homework problem that gave me the volume, and it was like the volume of a sphere. But you're going to need to know that too. So just, we'll talk about that in other videos, some ways that I found that are easy to memorize those things. So, but the biggest part is just practice. I haven't found a shortcut, just practice. So the area of a circle is pi r squared. But just like all of our other equations, we need to take the derivative of this equation with respect to time before we plug in any of our values, okay? So this is going to be the change in area with respect to time, so dA dt equals, now pi is just a constant. He's a multiplier, and so we don't take the derivative of him. We only take the derivative of variables. Now here, our area is changing, and our radius is changing. So those things we do take the derivative of. So we're going to say 2r, right? Because that's our normal way we would take a derivative. We bring our power down. And then our power here is just what? 2 minus 1, which is 1, and we don't write that because we just know that r to the 1 power is r. And then we have times the derivative of r times dt. So, or divided by dt. Now let's clean that up. 2 pi r dr dt. Okay, and so we already have dr dt, so we can say 2 pi, and our radius, they want to know when it's 37 centimeters. So 37 times 4, and then what I have seen is we do 2 times 37 times 4, and the answer then is 296 pi. We leave the pi because pi goes on like forever and ever and ever. Like there's a bunch of, like it's just a bunch of numbers. So if we were to plug in pi right now and get, it would equal just 929.9. But that's not really correct, because if you were building a bridge, and you plugged in this number early, your bridge would probably just fall down, because a lot of your numbers, they need to be as exact as possible. So it's just good like a good practice to get into the habit of doing this. So when r is 37 centimeters, so this is going to be, area is going to be centimeters per minute. We have our area changing at that rate. And oh, don't forget the 2. Remember, area is 2-dimensional. And volume, 3-dimensional, which means it'll be to the 3rd. Okay, so I'm going to stop this video so it doesn't get too long. I hope this was helpful, and we're going to get into even more word problems that are like even more fun, and you start realizing that you can figure out a whole bunch of stuff that you never thought you could figure out before, and this is only Calc 1, and so that means that it's going to get even better. And just keep practicing, because life is awesome. Okay, bye guys.